Okay, so again, just as a review, we're just going to practice simplifying these radical expressions, sort of what we did last time. So the first radical expression is the square root of 56, and then the second one is the cube root of 56. So take a few minutes, try to simplify those. Okay, how'd you guys do on these? Were they fairly straightforward? You guys having trouble still? Anybody have any questions as to where to start? Let's see. Okay. Um, so what I would do is, the first thing you might try to do here is if you're, just feeling like I want to do this the most convenient way possible, you might throw this in the calculator, and then you might just say that this is 7.4 or 7.48. But that's not going to be correct because we need to get an exact form. This is an approximation. Even if you took it out to 9 decimal places, it is not the same value as this number here. And one way that you could sort of see that is if we go ahead and do 56 minus the square root of 56 minus 7.48, 3314774. If they were the same value, when you take the difference, you should get 0. And yet the calculator is throwing us this really small number, and it's in scientific notation. So clearly, the calculator is not able to handle the exact value other than to say that, the square root of 56 is an exact value, and it's a little bit bigger than this decimal representation. So we don't want to go with the approximation here. We need to be able to do these by hand when we're simplifying these kinds of radicals that aren't a perfect square or a perfect cube and so on. So the first step is going to be to prime factorize. So I'm going to make a factor tree for 56. Okay, so 56 is going to be, maybe you think of this as 8 times 7. And then maybe you break up 8 into 2 times 4. I'm going to go ahead and circle all the prime numbers. 4 is 2 times 2, and 7 is also a prime number.
I think so.
Okay, so that means we can write 56 as we have 1, 2, 3 2's. So that's 2 to the third power times 7, right? That's the prime factorization. If you were to multiply this back out together, you would get your 56. Okay. But the thing you want to remember here is that the question that you've been given, or the number that you've been given, has a square root, and that's giving you the hint as to what we are trying to cancel out. So remember that the square root, even though we don't write it, has an understood 2 for its index. So we need to get an exponent of 2 on this value, which has an exponent of 3 currently, because we want the index of 2 on the radical to cancel out the exponent of 2, since those are inverse operations. So what we'll do instead is write this as 2 squared times 2 times 7. And that preserves the integrity of this expression, because 2 squared times another 2 would be 2 to the third power. So that's perfectly okay. What we can do now is rewrite the radical expression, which is the square root of 2 squared times 2 times 7. And you'll notice that the index of the radical is going to cancel out this exponent, but we're going to have to keep our 2 and our 7, the extra 2 and the 7, together, because they don't have a square. They don't have an exponent of 2. So they're going to have to stay locked in the radical symbol. So you could think of it like the square root of 2 squared, where now the radical expression, or the radical symbol, and the exponent cancel out. But we'll leave this as the square root of 14 right here. So since I've sort of run out of space, I'm going to just draw an arrow. And since this canceled out, you're just left with a 2 that is no longer inside the radical. But we still have this square root of 14, which we just have to leave alone. Since there's nothing else we can do to simplify this expression, we're going to say that this is as simplified as we can get it. And then remember, you can always check whether your initial value, or this initial expression, is equal to this expression by looking at their decimal approximation. So we're just going to grab our calculator. I can put the square root of 56 into the calculator, and it comes up with this decimal expression. And if I type 2 times the square root of 14, so 2 root 14 is the way you might say it, you get the same decimal expression. So that means that this is the correct simplification. Does that make sense, or does anybody have any questions? Well, the nice thing about me using this 56 again is that the first step is always going to be to prime factorize, right? So we've already done a prime factor tree, so let me go ahead and copy this one again. Maybe this time you were feeling differently about the prime factor tree, and you said, okay, well, this is 2 and 28, 2 is prime. This is 2 and 14, 2 is prime, and that's 2 and 7, and these are prime. Either way, you still get, whether you started off with 8 and 7 or 2 and 28, you still end up with 2 to the third power times 7. But since this problem is asking us to simplify a cube root, we can go ahead and leave this expression as 2 to the third power times 7, since we're trying to cancel out that cube root. So I'll go back to my actual work and not my scratch work, and I'll write in 2 to the third times 7, because this expression here is going to replace the 56, since they're equal in value. Then we can say, okay, we can split up the cube root over this product. So I can write this as the cube root of 2 to the third power times the cube root of 7. Now you want to be very careful that when you split up the cube root, that you don't get sort of lazy and forget to put the little 3 index. Because if you forget to type in the 3 in MyLabs Plus, you'll get it wrong, right? Because we're not dealing with the square root. So if you left off that index, you would be saying the square root of 7, but we're dealing with the cube root of 7. Okay, so that's just a little note. But in any case, this works out just like the other problem. The cube root index matches the exponent. So since those are inverse operations, they will cancel out. We can cancel out the radical symbol and the exponent, which leaves us with a 2 times the cube root of 7. And since we don't have a exponent of 3 here, that's as simple as we can get this. And again, we can check ourselves in the calculator by taking the cube root of 56, and we get about 3.82 blah, blah, blah. And then 2 times the cube root of 7, and we get about the same value. So these are the same value, which means that we have correctly simplified this expression. Any questions there? Are we starting to get a handle on those? Okay. Well, I started to talk about complex numbers last time. And basically, we have this expansion of our number system. I said, you know, in ancient civilizations, there was a need to invent numbers for keeping track of different things that you own, right? You might want to know how many cows are on a particular plot of land. You might want to know how many, I don't know, bushels of bananas that you're trying to exchange with somebody at a market, right? But in any case, numbers were an invention that allowed us to categorize things in the real world, right? And actually count their quantities and know how much, how much we have, how much we're trading, and how much is being exchanged, right? But it is very much an invention. So in ancient times, negative numbers were not widely used, but eventually they came to be used because they're useful for describing debts. And so whenever there's a need for an expansion of our number system, then one is invented. And so the complex number system is this natural extension of our real number system that allows us to work with numbers of the form the square root of a negative number. Okay, because we saw that the square root of a negative number implies that a number squared gives you a negative. So this is just a note here on what the imaginary unit is. But remember that if we had, for example, this question, the square root of negative 25, and that is equal to some number. This question implies the equation, right? Or the statement that some number, when you square it, gives you negative 25. And from last time, we made some guesses. We said that, okay, maybe x could be 5 or x could be negative 5. But if x equals 5, that implies that 5 squared, which is 5 times 5, gives you positive 25. We don't usually put the plus sign in front of it, but just trying to make this absolutely clear that this won't be the correct answer because we're trying to get a negative 25. And then likewise, if we had negative 5 squared, then that would be -5 times -5. But since a negative times a negative gives you a positive, that can't be the answer to this equation either. So those don't work. So because our square root operation is sort of doing something funny here, and implies that something squared should give us something negative, then we sort of have to figure out a way to deal with this negative square root. Okay. So to deal with numbers of the form the square root of -a, what we can do is we split -a into -1 times a. So that means that the square root of -a is equal to -1 times a inside the square root. And then by the property of radicals that we saw last time, we can split this radical up and call this the square root of -1 times the square root of a, whatever that number is. And then we're just going to say, like, this is the guy that gives us problems. So we'll call this the imaginary unit. And we'll just call that the variable I. And we'll leave this square root of a as the real part. All right, so we have a real number times the imaginary unit. And that's as far as we can simplify it, right? So if I knew what the value of a was, then maybe I could simplify the radical the way we've been doing last class. So as a concrete example, to finally, put this to bed, the square root of -25 will be handled the exact same way as using this sort of like formula. What we can do is we could say that this is going to be the square root of -1 times 25. That can be split up into -1, the square root of -1 times the square root of 25. That we can then call the square root of -1 the imaginary unit. So we'll just put an I here. And then we can simplify this number in particular just because the square root of 25 is a perfect square. That's going to be I times 5. But by convention or just by tradition, mathematicians treat this imaginary unit sort of like a variable, and we're just going to stick it in the back. So since this is multiplication, order doesn't matter, but typically we'll write this as 5i. Okay. So it turns out that 5i is the square root of -25. So that's how we're going to go about simplifying these negative square roots. Okay, so what I want to do is give you guys some practice problems and throw you into breakout rooms, because I think that process, since we simplified a bunch of radicals last time, this process should be very simple, with the exception of the new imaginary unit that we have to put in there. So let's get some practice in. Okay, and let me see. So the instructions for these problems might say, write the number as a product of a real number and the imaginary unit I. So we might want to do the square root of negative 16, the negative square root of negative 9, the square root of negative 29, the square root of negative 176, negative 125, the square root of that, okay. So I'm going to create 2 breakout rooms. You guys, obviously, I know how this works. You guys will work on your own a little bit to work through these, but as you get stuck, ask each other for help or for guidance on, how do I approach this? Okay, and I'll be in to check on you guys in a bit. And those breakout rooms are now open, so go ahead and accept the invitation. Okay. So I sort of want to go through these one by one, just so that we all get a handle on them. I think that most of us got through at least the first 4. Maybe some of these were starting to get a little bit tricky, like number 3, maybe number 4. But in any case, I think that seeing them will be super useful for us. So let's start with the first one, which was the square root of negative 16. Now I know that when I wrote this out, what I did was I separated this into, well, let me write it this way. This would be the long way. I separated this into the square root of negative 1 times 16. Then I split up the radical like so. I know that this is the imaginary unit now, and I know that I'm multiplying that by the square root of 16, which simplifies to 4. So in that case, we would just get 4i. Okay. Notice that the 4 no longer has a square root because we've used up that symbol, we've used up that operation. So since we've used it, it's gone. You should not put a square root symbol on the 4. You will confuse yourself if you throw a square root symbol on when you've already used it up. Okay, so just be careful with that. The answer should be 4i. But what you'll notice is that typically what I tell students to do once you get proficient at it is that if we notice that we're taking the square root of a negative number, then I already know that this is going to be an imaginary number. So I can just think of it as I times the square root of 16, which is I times 4, which is just 4i. Okay. So that's sort of like the shorthand way that I'll usually write out the problem. I will pull the negative number out and just call that I. What's really happening is that I'm saying that the square root of negative 1 is going to come out of this product, and I'll have an I there, right? But this is the way my shortcut method for doing it. And then once you get good enough at that, for some of them, for which you can already tell that that's a perfect square, you can say that, okay, well, I know the square root of 16 is 4, and since it's a negative 16, that's going to be 4i, right? But you'll develop that proficiency as we go. Just make sure that you understand the concept of why we have the I here, and it's because of this factor of the square root of -1, that imaginary unit. Okay, so for number 2, we were looking at the negative square root of -9. Well, here's one of those cases where I could say at least this part here, 9 is a perfect square. So I know that that is going to be 3i since I have a negative inside there. But I still have this negative on the outside. So negative 3i is the answer for number 2. Is anybody confused or have any questions about that? Yeah, because once you sort of get it down, this is what you'll be doing. You know, I won't have to see you write it out the long way. This long way is really just so that, you know, if you understand how to do it the long way, then you really understand why it is that we can go from this to this so quickly.
I noticed on the homework that if you do the help me solve this, it teaches you how to do the short way also.
Oh, does it?
Yes.
And I bet that depends on the numbers that come up on that particular problem, though. Because for some of them, like number 4 that we did here, well, you know what? I think that the computer does tend to show you the short way, but what students think about that usually is that they're skipping steps. And so it's sort of hard to follow. Um, at least that's the consensus among all the students that I've worked with throughout the semesters. Sometimes they do that. And if you already sort of understand the reasoning behind why they can do this, go from 1 to 2, like step 1 to step 2, then you don't have to necessarily write out 1, 2, 3, 4 different steps, right? Because if you could do this in your head and you wrote this down on your test, for example, I would understand exactly what you did in your brain. I don't need to see all of this. But I show you the long way so that you can understand the reasoning. And then once you understand the long way, well, then you can start cutting corners. But not until you really understand this should you be cutting corners, because that's when mistakes happen and then students start inventing math. And usually there's nothing wrong with inventing math as long as it's consistent with all of the rules that you've learned up to that point. Inventing inconsistent math is the real problem. In any case, we're doing the square root of -176. So for me, 176 is not an obvious number where it has an obvious square root. So here I might go ahead and say, let's ignore the negative for a second. Or maybe, you know, I'll do that thing, my trick, where I say, I know that this is a negative number, so I know that I'm going to have an imaginary unit here. So really I'm dealing with the imaginary number or the imaginary unit times the square root of 176. So now I just have to simplify 176, and we do that the same way we did all of the other radical expressions. So this will be 2 times something. 176 divided by 2 is 88. Well, that's really nice because that's 8 and 11. 11 is prime. And I know that this is 2 and 4, and that this is 2 and 2. So I know I can rewrite this as 2 squared times 2 squared. So 1, 2, 3, 4, that's 4 2's times 11. And I also know that this square and this square are going to get canceled out. So I could write this as 2 times 2 times I. And then this guy is not going to get canceled out since it doesn't have an exponent of 2. So that stays in the root, like so. Well, since I'm multiplying 2 times 2 here, might as well just keep it as 4. So let me just say that I'm going to go over here and write this as 4I root 11. And, as slang, I just say 4I root 11 because it's just a mouthful to say 4 times I times the square root of 11. So 4I root 11, I will understand what you mean. And because this is just multiplication, it really doesn't matter the order that you write these in, these factors, but the conventional order is that we have the real number part first, the imaginary unit next, and then the last thing that we have is the radical. Now, I think it was Kelly that was saying that she got 4 root 11 times I, sort of like this, 4 root 11 I. And this is correct, but what I'll say about writing it this way is that when you're typing this into MyLabs Plus, sometimes students make the mistake of extending the radical.
Okay.
So that the I is inside the radical. And that would be incorrect. So if you do write it this way, it wouldn't be wrong, but in MyLabs Plus, you want to be careful that that I is not inside the radical symbol.
Okay.
So by convention, we just tend to do the real, the imaginary part, and then the radical expression. I very much apologize for squeezing that all in at the bottom there. Let's see if we have something similar here. Negative 125. Okay, and there's other ways of sort of breaking these numbers down if you wanted to. I mean, we could say that this is I root 125. And then you might say that this is I times, and then I know that this is 25 times 5. So this is sort of me not doing the prime factorization, me knowing that, if I have a quarter and I have 5 quarters, I'll have 125. So the reason why I would do that is because I know that the square root of 25 is just 5. So I have I times 5 times root 5, and then we can just put it in our conventional order, which would be 5I root 5. Any questions on that one? I know that I did that sort of, I sort of breezed through it. So let me give you guys a moment to catch up. I'm going to take a swig of water, and if you do have questions, go ahead and just hit me with them. Or comments, it doesn't have to be necessarily a question. It could be like a reflection, or just something that comes to mind about this. Okay. One note is that you can't check these in the calculator, at least not directly. Because you'll notice that for most calculators, if you take the square root of a negative 125 or a negative number, let me go ahead and zoom in, you'll get this error. Error, non-real answer. Okay, and let's see if I can do this. This is my iPhone. If I take, let's say, I could do the same number, right? 125, and then I'll make that a negative 125 and take the square root of it, and I get an error. So what I'm trying to point out is that we can't check these directly in the calculator because you're going to get an error because the calculator cannot deal with imaginary numbers. At least these calculators. There are some really fancy, expensive calculators nowadays that can, but I seriously don't expect you guys to go out and buy those things because, again, they're super expensive. So what we can do to indirectly check is that we can just check the real part of our simplified expression. So ignoring the I, we can write 5 times the square root of 5 in the calculator, and we get this thing. So we're taking the real and the positive part, and we'll just compare it to the positive square root, right? So the square root of positive 125. And if those come out the same, then we should be good. Just keep in mind that because this is a negative, the square root of a negative number, we should have an imaginary number when we simplify. Does that make sense? So you can check the real / positive part. And that's one of the really nice things about math is that there is a way to check the work yourself. Entonces, we're moving on. The negative square root of negative 48. Okay, well, this is the way I would do this in my head. I would say, first off, you know what it is if you heard Drake. Okay, and then we're just going to move on to the negative I root 48. And then we can go ahead and take care of this positive root. 48 is going to be what? Is that 6 times 8? I'm zoomed in still, my bad. 6 times 8. 2 times 3. 2 times 4. Boom, boom, boom. 2 times 2. So we have 1, 2, 3, 4. So that's 2 squared times 2 squared. So 1, 2, 1, 2, and then a 3. Which means that when I take the square root of all of these guys, the square root will cancel out this guy and this guy. So I'll have 2 times 2 on the outside, and I'll have the root 3 left over. So this is going to be negative I times 4 times root 3, but we'll go ahead and rearrange that so that it's negative 4 I root 3. And then I'll just put a little squiggly line to separate my scratch work. How do you guys feel about that one? Does that one make sense? Or are they getting any crazier? Okay. Let's look at number 7, which is the square root of negative 98. And then I'll put 8 here, which was the negative square root of negative 55. Yeah, we're just going to pull the negative out here. I'm going to call this I root 98, and then I'll just work on the positive radical. So that's 98. What would that be? 2 times 49? 7 and 7. So that's 7 squared times 2. So if I take the square root of 7 squared and the square root of 2, then those cancel out. So I should be left with a 7 on the outside. I have my I, and then root 2. You double check that because I've been known to make mistakes. Becoming a math teacher is not one of them. And those check out. This one, go ahead and pull that negative outside of the root and call it an I. So we have negative I on the outside, root 55, as opposed to root 66. And then 55 breaks down into 5 and 11, both of which are prime, neither of which have a square. So we can't simplify that any further. So we're just going to leave that as negative I root 55. All right. How are you guys feeling about that? Let's just take a moment to reflect and discuss any comments or concerns with these particular problems. Do you guys have any questions, or were there any like weird things that came up that you wanted to ask me while you were working them? Are you guys starting to feel a little bit more confident about them? Or is this the kind of thing where, you want to practice a little bit more before you feel comfortable talking openly about them?
I feel pretty good.
Okay, cool. We got one. At least one. I know that there's probably a few of you guys that are just a little bashful.
I'm okay. I'm okay too.
Yeah, I got two. So 2 out of, let's see, if 2 out of 15, 14 of you guys right now, that is times 100. 14% of the class is comfortable with this right now. So
I think doing a little bit of the homework and then learning this lesson now, it is helping. Sorry, I had to step away for a second.
all right, so that puts us at 3 divided by 14, which
Thank
is about
you.
21% of the class feels pretty comfortable. Okay. I just like to play around with math sometimes because why not? Well, let's just move on to the next thing, which is very similar. There are going to be times when we solve quadratic equations, which is what we're working up to, okay? We will solve quadratic equations. And we've already seen some of them. Some look like this. X squared is equal to 49. Does anybody know what x has to equal?
7.
Yeah, that's one of our answer choices. So 7 works. Does anybody know another number that you can square and get 49, positive 49?
-7.
Yeah, because we know that -7 times -7 also gives you 49. But that one was really nice because we're just dealing with positive numbers there. Some of them look like this. X squared is equal to, let me do -81. So in this case, we sort of have to solve it using something called solve using the square root property. This is another way of thinking about how you solve this first one. So let me talk about the square root property just really briefly, and we'll talk about it again when we really get into this. I said that when you looked at an equation like this, x squared equals 49, that's related to the equation, the square root of 49 is what? But the square root property basically says if you have an equation of the form x squared is equal to, I'm going to use k as my constant. That what you can do, this is sort of like our principle of addition and principle of multiplication. as long as you do addition to both sides of the equation, you are fine, right? Nothing changed, you would still get to the right answer. And as long as you multiplied or divided the same number on both sides of an equation, it wouldn't affect your results. Well, the square root property says that when you're given an equation that looks like this, and we want to cancel out the square, what we can do is take the square root of both sides. So this is sort of like a new trick, a new tool in our toolbox of tools that will solve equations. So you can think about the square root property as just take the square root of both sides of the equation to cancel the exponent of 2. So I know this is a lot of writing the same thing. So we would have something like this, where now the square root symbol and the square cancel out, and we're left with x is equal to whatever the square root of this number k is. But because square roots, when you take the square root of a squared value, you can have two solutions. One is a positive and one is a negative. You have to remember to put either a plus or a minus symbol here. So this symbol where you have the plus sign above the negative sign is called plus or minus. And it's just a condensed way of writing two solutions. So the solutions here would be x is equal to whatever the positive square root of k is, and x is equal to whatever the negative square root of k is. So in practice, this equation that we saw right here, the x squared equals 49, if I take the square root of both sides, the square root of 49 is going to be that plus or minus, so the positive or the negative 7. Okay, so that's one thing that you're going to have to watch out for quadratic equations. This exponent for quadratic equations is sort of telling you how many solutions you might have. So you can have a max of 2 solutions. Okay, but really, how do we solve this guy? Well, let's look at that. So if we are solving the equation which is x squared equals negative 81. What we're going to do, what's up?
My internet keeps cutting out and the quality keeps going like really bad. Is it okay if I rewatch the footage later?
Yeah, absolutely.
I can't see the words you're writing.
Is anybody else having the same difficulty?
No.
Okay. So if ever you're having difficulty hearing me or seeing what I'm writing, and it's like an internet connection issue, feel free to just drop out, send me a message in the chat. I'll read that. And obviously the video will be up later. So I know it's like really frustrating when that happens. We just have to deal with it since we're remote and still in the middle of a pandemic. But just go back and watch the video later, as opposed to staying in the classroom and it being all frustrated with the internet. Okay. So so if we're trying to solve this thing, x squared is equal to negative 81, it's sort of harder to think of what is the number here that when we square it will give us a negative number. There's 2 approaches here, but I'm just going to show you this using the square root property, which again is just equivalent or very similar to our addition principle or multiplication principle. And the square root property just says, okay, I'm going to write the equation over, and I'm going to throw a square root on both sides of the equation. Once I do that, I know that the square root of x squared is just going to be x. And I also know that now I need to have a plus or minus over here because I should have two solutions. Now all I have to do is simplify the square root of negative 81. And since we've been simplifying these guys in the last problem set, well, this will be x is equal to plus or minus 9i. And again, this is just the condensed way of writing it. In MyLabs Plus, sometimes, if I could spell, sometimes gives the plus or minus button. But when it doesn't, then you'll just have to write your solution set as, so here's my solution set. Solution sets are always written in the curly braces. I'm pretty sure they write that out for you. But then you just have to put negative 9i, comma 9i. Those are the two solutions. Does anybody have any questions about that problem? Okay. We're going to get back to solving quadratic equations properly, but there are certain solutions. Looks like I need to rip these pages off. Certain solutions or numbers are going to be these complex numbers. So the standard form of complex numbers is a plus bi, where usually you'll have some number here, which will be a real number. And then this guy attached to the I, which is the imaginary unit, well, that's going to be your imaginary part. And that's why we call them complex numbers, because they're a complex of both a real and an imaginary part. So for certain problems, let me see if I can think of one. How about if we need to solve the quadratic equation? And the equation looks something like this. 2x plus 7 squared equals negative 28. Well, this one looks a lot more complicated than the other quadratic equation that we were given. Well, you'll notice that this thing on the left-hand side of the equation is squared. And we know how to cancel out the square. Now, we cannot get to the stuff inside the parentheses until we can get rid of that square operation. So getting rid of that square operation is going to be the first thing that we need to do. So the square root property says that if I have something squared, and that's equal to some number, that I can just take the square root of both sides. And then I'll get this guy by itself, whatever that x is, and I'll have plus or minus the square root of k. So for now, I'm going to treat this whole thing like it's our variable x. And so what I can do is 2x plus 7 squared is equal to negative 28. What I can do is take the square root of this whole side and take the square root of this whole side. And now I know that the square root and this square will cancel out. So I get 2x plus 7 is equal to plus or minus the square root of negative 28. Well, now I don't have a square to worry about. So what I can do is think about this like a linear equation. And I could just solve it by isolating x. So we'll have more practice with this here in a second. I'm just going to walk you through the process. The first thing I'm going to do is I'm going to use the addition principle to subtract this 7 over to the other side. So don't mind me. I'm going to subtract 7 here. I'm going to subtract 7 here. Since this is a radical expression and this is just a whole number or a constant, I'm going to not combine them. But instead, I will write this as 2x is equal to negative 7 plus or minus the square root of negative 28. Then if I want to get the x by itself here, I'll divide this whole side by 2 and divide this whole side by 2 so that these 2's cancel out. And now I know it looks complicated, but I'm going to give you guys some practice problems here in a second to see how do we go about simplifying this weird monstrosity over here. So let me just write x is equal to negative 7 plus or minus the square root of negative 28 over 2. Okay, so the idea is, how do we simplify this? This weird expression on the right-hand side of our equation. And it turns out that, this is a number. Well, it's two numbers. One is going to be negative 7 plus the square root of negative 2i over 2. And negative 7 minus the square root of negative 28 over 2. But we need to sort of simplify this step by step. So the first thing I'm going to tell you to do is, 1, simplify the radical, which is this guy here. So I know that the square root of negative 28 is equal to I root 28, and then I just have to worry about, figuring out what that simplifies to. So 28 divided by 2 divided by 2. Okay, so that's going to be 2I root 7. I'll give you some time to figure that out. But I skipped all the steps in between. So the second step is just going to be to replace the radical with the simplified form. So I still have -7 plus or minus, but now I'm going to plug in the 2I root 7. Right where the square root of -28 was. And it's still over 2. Okay, and then we're going to split up the fraction. What I mean by that is that if you have, let's say, a plus b over c, a fraction like this, and it could be a subtraction symbol, we can split this up into a over c plus b over c, having the same denominator. So really, you're thinking about it like this. I have this -7, and I have plus or minus 2I root 7. They're both over this common denominator. So I'm going to split this up into -7 over 2 plus or minus 2I root 7 over 2. And the last step is going to be reduce the fraction if possible. Okay, so now we're sort of looking at two numbers here. -7 over 2 cannot be reduced, so we're going to leave that as -7 over 2. But if you're looking at this weird monstrosity, is there a common factor on the top of the fraction and on the bottom of the fraction that can be canceled or reduced?
Number 2.
Yeah, the 2's, right? Be careful here because sometimes, if this was an 8 or some other even number, students will want to reduce that number that's inside the radical with one of these numbers that's outside the radical. But we can only reduce numbers that are outside of the radical. So since we have a factor of 2 here and a 2 here, 2 divided by 2 is 1. So really we're just left with I root 7. Now, just to double check, this fraction cannot be reduced because 7 and 2 are mutually prime. That means they don't have any common factors. And then I root 7 can't be simplified anymore because 7 is prime, and so we cannot factorize and bring anything out of the radical expression. Okay, so since there's nothing else we can do to sort of process this expression and make it any simpler, this is your answer, and it's in the form a plus or minus, I'm going to put IB here, or BI. So this would be the solution. Does that seem like a lot?
Yes.
Yes. Which is why I have a set of problems that is just going to be focusing on simplifying expressions that look like this so that you guys can get practice. And then we'll add on the solving the quadratic equation. Okay. But did anybody have any confusion or get lost at some point along this process? Okay, let me throw one at you that should look similar. So practice simplifying. Yeah, and we just have to get used to this because when we start solving some quadratic equations, some of them have really ugly looking solutions. So we need to simplify 2 minus the square root of negative 28 over 2. And again, I'm just going to recap the steps for simplifying something like this. The first step is to simplify the radical. So take a moment to do that. The second step will be to replace the radical with the simpler form, or the simplified form. Once we've done that, then we can split up the fraction. And we usually split up the fraction wherever the addition and subtraction symbol is, right in between these two terms up here. And then the last step will be to reduce either fraction if possible. Is anybody just completely stuck?
Would this be, I got negative I square root of 7.
For this side, right?
Yes.
Yeah, let me see. Let me work this out real quick. 28, we just did that. I'll just do it again. That's 4 times 7. So that'll be I and then we'll have a 2 root 7. And so I'm going to make that replacement here. This guy gets replaced with this guy. I'll have 2 minus 2I root 7 all over 2. Is that what you had? At least that's for the second step. Then we'll split up the fraction. So remember I said, think about the 2 terms on top as 2 minus 2I root 7. So we're going to put those both over this denominator. So 2 over 2 minus 2I root 7 over 2. So we've split up the fraction now. And now we can reduce the fractions if possible. So we have this term and this term. And 2 divided by 2 is how you want to think about the first one. And that's just going to be 1. So you could think about these as canceling out, but they don't cancel out to nothing. It's canceled by division. So 2 divided by 2 is 1. And then over here, these cancel out. It's still canceled by division. So 2 divided by 2 is 1. And all you're left with is the I root 7. So it should be 1 minus I root 7. And that should be the end of that story. Is that what you got? Was it Pamela?
Yes.
Okay, cool. Was there anybody else who was just like flat out confused or needs me to like reiterate something or? Was that okay? Are we, these 4 steps, you know, we're gonna walk slowly through them, but then as you start to get comfortable, you will speed up. So let me give you some more problems, some more practice problems. That was one. More practice. 2, 6 plus the square root of negative 48 over 2, 3, negative 2 plus the square root of negative 12 over 16. And then 4, negative 4 minus the square root of negative 108, all of that over 2. But this time I am going to throw you guys into breakout rooms so you can work amongst yourselves. Let me go ahead and recreate the breakout rooms. All right, the rooms are now open. Make sure you lean on your classmates to see, you know, where are the issues coming up? Where do we need some help? And just reach out when you need it. I'll be in to check on you guys in just a moment.
If you're talking, I can't hear you.
Okay, I forgot that when it brings me out of the breakout rooms, it always puts me on mute for some reason. Okay, but just to recap what I was saying when you saw my hands dancing on the page. So when we simplified this weird expression, which admittedly is very weird, 6 plus the square root of negative 48 all over 2, we did some processing. We simplified the radical, and that turned into 4I root 3. Then we split up this fraction, into 6 over 2 plus 4i root 3 over 2. And then we just simplify each of these fractions. So 6 divided by 2 is 3. And the 4 divided by 2 here just leaves you with a 2. And we're just going to keep our I root 3. Now, Yvonne asked a really good question. And that was, can you combine the 3 and the 2 here? You want to be very careful not to combine these terms because one part is real and one part is imaginary. So we have apples and oranges, just like when we had variable terms and constant terms. We cannot combine a real part with the imaginary part through our ordinary addition. So we just have to leave the expression the way it is. Okay. So then we simplified this expression, right? And we should have gotten negative 1/8 plus I root 3 over 8. Yeah, were you guys able to get this in the other breakout room? Okay, good. And there it was just a matter of, once we simplified the radical, again, you're always starting with the radical expression. And you might ask why, or might not, but in any case, think of it like order of operations. We want to work on everything in the grouping symbol first. And here we have two grouping symbols. One is the fraction bar, which we have a bunch of stuff on top and a bunch of stuff on bottom. So we just focus on the top. But then within the top of the fraction bar, we have another grouping symbol, which is the square root. So that's why we're going to take care of simplifying that first. That simplifies into 2i root 3. And then once we've done that, we can split our fraction apart, keeping that same denominator, and then reduce the fraction. So negative 2 over 16 is the same thing as negative 1/8. And then the 2 over 16 here also simplifies into 1 over 8. But if you multiply 1 times I root 3, multiplying by 1 does not change the value of the numerator. So we're just going to leave it as I root 3. And then finally, let's go ahead and do this last part. Let us see. We're going to simplify the radical. I don't know what this simplifies down to, so I might use my calculator here. I'm going to have negative 4 minus something all over 2. So I know that this is 108 divided by, sorry, that's 180. Did it again, 108. I know there's a 9 in there. A 9 and a 12. So there's a 9 and a 4. There's a 36. Okay. So I'm going to divide this by 36. 36 and 3. So one thing that you might do is call this I root 108. And then you might call this I root 36 times root 3. This is me cutting corners. Even if you didn't do it this way, you would eventually get 6i root 3. And then let me just double check to make sure that that works. The square root of 108 and 6 times the square root of 3. Same value. Okay. So this is going to be what I replace this with, 6i root 3. And remember, if you want to learn how to cut these corners the way I do, then you have to come to Math World. There's just not enough time for me to show you guys how to do that here in class. In any case, we'll go ahead and split up this fraction, negative 4 over 2 minus 6i root 3 over 2. And then we can only simplify this part to 4 over 2 is just negative 2. We can simplify this part too as well. So that's going to be minus 3i root 3. Is that what you guys were able to get? Or were you able to follow along and not get too lost?
Yes.
Okay, good. Well, let's take our 10-minute break now and come back at about, let's just call it 2:15. Okay, so enjoy your break. Okay, welcome back to the podcast. All right, we've been working on simplifying radical expressions and radical expressions that might lead to imaginary numbers, and then these weird complex expressions that look something like this. which can be simplified down into some complex number of the form a plus bi, or ib. Remember, that's just multiplication, so the order is not going to matter there. But the reason why we've been doing that is because if I threw you into quadratic equations and learning how to solve those just at the very start of this class, then once we got some weird looking solutions like that, it would be like, what the hell is this thing that I'm even looking at? How do you expect me to simplify that? So I wanted to build that up into baby steps where we were simplifying real radical expressions with real numbers inside. And then with negative real numbers inside, that resulted in an imaginary number, and then built up to these weird looking complex numbers that have both a real and an imaginary part. But that is all leading up to quadratic equations, since sometimes the solutions of quadratic equations look funny, to put it mildly. And quadratic equations, they occur in real life whenever you have some sort of, well, when we start to graph them, you could think about it like a process. For instance, let me draw a little graph here. And let's say that this is time in months. And that, well, maybe not time in months. Maybe we're going to think of this as amount of rainfall. Yeah. And let's think about maybe plant growth over here. And I want to track the changes in plant growth across rainfall. This is something that, an ecologist or even a gardener, a horticulture or agriculture person might be thinking about, right? Because during the dry season, let's say that here near zero, let's say that's zero moisture, zero rainfall, that we would consider this part of the graph, the dry part. And then eventually it would become a little wet in the soil or the environmental conditions. And then maybe it would become very wet. And that plant growth is sort of low here. And then as you get more moisture in the soil or in the environment, then that plant growth will increase. But then when it becomes very wet and the water is sort of like you've got waterlogged soil, you're going to get an environment that's going to have more mold, more fungi that are growing, that are going to inhibit the growth of the plant. So then you have something that looks like this. Okay. So it turns out that whenever you have a humped graph like this, it's not linear. But this general shape here, if I were to just model it with a sort of a U curve like this, we call this shape a parabola. And it turns out that when you graph quadratic equations, you obtain a parabola. Okay, but maybe I'm getting a little ahead of myself. We're going to talk about graphing quadratic equations a little bit later on. Right now, we're just dealing strictly with the algebra, with manipulating numbers and simplifying expressions. So algebraically, quadratic equations typically take the form ax squared plus bx plus c is equal to 0. we call this standard form. Standard form of the quadratic equation. Okay, and here A, B, and C are real numbers. The key here to identifying a quadratic equation is that you have this term here, x squared, right? So for linear equations, we had something like mx plus b, or just something x plus some other number, right? But now we have this squared term, or the variable is squared, cuadrado, right? So that's why we call them quadratic equations. So as long as we have a squared term in our expression, and that's the highest degree of the polynomial, then we can identify it as a quadratic equation. And the idea here is that just like with linear equations, we want to figure out what x is. So we need to find out how to solve for x, not x squared. We want to get x by itself. And that's going to be sort of the main concept for solving quadratic equations, because you'll see that the steps that we take to solve a quadratic are not the same steps we would take to solve a linear equation. Okay. But luckily, let me go ahead and leave this here. I think if anybody is still writing. Okay. Luckily, I've already previewed one of the ways in which we can solve quadratic equations. So here's going to be the first method. And we call it using the square root property. Well, I think it's natural to talk about the square root property here, since we've been working with square root expressions this entire time. So if I needed to solve x squared is equal to 16. You might be thinking to yourself, well, Mr. Aguilar, this doesn't look like a quadratic equation because it doesn't look like it's in standard form, where standard form is ax squared plus bx plus c equals 0. Well, if I wanted to, I can manipulate this in the same way that I manipulate any other equation. So I could move the 16 over and subtract it to the other side, and then I could call this x squared minus 16 is equal to 0. And you don't have to write this down. This is just for illustration purposes. And then I could say, okay, this is x squared plus, well, this is bx. So what if I just put 0 times x there, minus 16 equals 0. Well then, yeah, sure, a is equal to 1, b is equal to 0, and c is equal to negative 16. So you could manipulate your equation to get it into standard form, but there's an easier way to solve this, right? And that's why I showed you guys the square root property earlier. So if we have a quadratic and it's not in standard form, but it sort of looks like we can just use the square root property here, then that's what we'll do. It's going to be a way easier method for solving this. So what I'll do is just take the square root of both sides. Again, the reason why we're doing this is because the square root and the square, so the exponent 2, are inverses and cancel. They cancel out. So as long as I remember how the square root property works, I can say this cancels with this. X is equal to plus or minus the square root of 16. And then I can just worry about simplifying that square root expression. So x is going to be equal to plus or minus 4. So my solution set here is -4 and +4. But when you type this into MyLabs Plus, you just have to type in -4, comma, +4. Does anybody have any questions about that? Okay, I want to give you guys a couple of these to solve on your own. So solve using the square root property. X squared is equal to, let's go with negative 144. 2. And then challenge yourself by trying to solve this next one. X plus 5 squared is equal to 16. And then if you're feeling really froggy, (9x) plus 7, that whole quantity squared, is equal to 11.